Hello, students, and welcome to Week 6 of Creative Engineering. Today we are going to be developing a solution to the clean water shortage problem, and you are going to get to use the skills that you've been developing over the last few weeks in eSchool to solve a real-world design challenge. We have learned about the challenge of lack of clean water around the world. We have learned about modern technologies that are helping to solve that problem. But not all technologies are high tech. What? So, at this time, and with that in mind, it's time for your Do Now. You will look at the 4 pictures in your Do Now on your digital worksheet. Drag a plus sign into the box with any that you consider to be a technology. Pause the video while you do this, and then press play to continue your video lesson. Welcome back, guys. I hope that you had a fun time thinking about what is technology. So on your digital worksheet, there were several items that are technology. And on this, hopefully you chose all 3 of the technologies. The only item that is not technology is the tree. And the tree would be considered a resource. Long before engineers solved water shortage issues with wells, filtration systems, straws, and solar power, they solved it with this and this. Maybe you've heard about these. These are examples of Roman aqueducts. And these were a means by which the Roman people, without any solar power or electricity or pumps or special filtration systems, brought clean water to their cities, which brought health and well-being to their residents. Watch this video to learn a little bit more.
Aqueducts are not that complicated in theory. That is that water seeks its lowest level, and therefore that you can run water down a slope from any area to another area. So that's a pretty simple premise that everybody would have known. But that the practice of creating an aqueduct is another thing.
The Romans engineered their aqueducts to approach the city on a gradual declining angle, or gradient. That gradient was just several inches every 100 feet.
The slope of the aqueduct had to be calculated from great distances, 20, 30, sometimes even 40 miles, from the source in the mountains to the cities themselves. That had to be consistent. They couldn't deviate from it, regardless of what the terrain was.
To maintain the water's precise descent through high mountains, Roman engineers dug perfectly angled tunnels through them. When the pipelines reached low valleys, they were elevated on stone walls. If the walls needed to be higher than 6.5 feet off the ground, the Romans saved building materials while still adding strength by perfecting an ancient engineering concept, the arch.
The arch revolutionized architecture in the ancient world by permitting far greater spans than had been allowable before. They basically changed the spatial conception totally of Roman architecture.
Arches were built around a temporary wooden framework that held each stone in place until the keystone was laid in the center. The keystone evenly distributed weight down each side of the arch, allowing builders to stack additional stones above it.
Arches are improvement upon building just a straight wall in a variety of means, both in terms of their efficiency and in terms of their strength. The arch, of course, takes much less material to build. Arches are very strong at supporting things like roofs and aqueducts and whatever you want to put on top of them.
A 6-mile column of arches carried the Aqua Claudia across the valleys on its way to Rome.
The aqueducts would have had a covered roof, but of course if you could take the roof off, you could see the water like an open river coming down towards the city.
After reaching the city, each aqueduct emptied into 3 holding tanks. One for the public drinking fountains, a second for the public baths, and a third reserved for the emperor and other wealthy Romans who paid for their own running water, a concept that was well ahead of its time.
Basically, every home by the 1st or 2nd century AD of any means had running water. This is astounding because the entire span of the Middle Ages didn't have.
So as you can see, the Romans had a pretty advanced system. Just to give you a better idea, here is a diagram that shows how these aqueducts were set up. So you would have a basin and conduits with vertical drain shafts that would collect mountaintop rainwater that you can see right there. Also, you have a lake that's providing additional water, and these are both seated higher than the rest of the aqueduct. Then you have the conduit, which could be several different structures. Here it shows arch structures, which carry the fresh water across valleys and over built-up city areas or along existing roads. The direction of the hill is always downward. At times, though, you would have pressurized pipes, which involved inverted siphons that sent water under its own pressure down one side of a valley and up the other side. But you could only bring the water back uphill if you had a sharp drop to help it get momentum to push it back up the hill. Here is an excellent 3D model of an aqueduct system. I want you to pay close attention to how the engineers built all the different features of the aqueduct here, and I also want you to pay close attention to how it has been 3D modeled.
The challenge for the Roman engineers was to keep the water flowing at the same speed on its entire journey. To get around hills, they dug trenches along the contour lines and covered them with bricks and earth. To cross wide valleys, they funneled the water down through lead pipes and up again on the other side. To conquer high mountains, they dug deep tunnels right through them and shafts in their roof for ventilation. To cross long distances on even ground, they built flat walls with a trough in the top. And to channel the water into Rome without obstructing traffic, they built the majestic arched aqueducts we know today. These plumbed into a network of fountains that fed water to 1 million Romans. Today, Rome's fountains are still safe to drink from. And because they always keep the water flowing, they stop the city's pipes from clogging up.
So that's a really good look at how the aqueducts were made. Also, it is a good demonstration of a 3D model of an aqueduct, and that's something you're going to need to know for later in our lesson. So aqueducts use no electricity, pumps, or hydraulics. They use basic architecture, tunnels, slope, and the power of gravity to move the water. So what did the Roman engineers have to know in order to build their aqueducts? They had to know where their water source was. They had to know the terrain between the water source and the city. They had to know the slope needed to keep the water moving gently downhill. And they needed to know where to build tunnels, where to build walls, and where to build the large arches. Roman engineers had to calculate the mathematical concept of slope in their aqueduct in order to be sure the water was running downhill. Pause the video for just a moment while you complete the notes for this section. So I want you to fill in the notes. There's only a few, and as soon as you finish filling in the notes in the direct instruction section of your digital worksheet, then press play to continue this video lesson. Welcome back, guys. I hope that you got your notes jotted down and that you did your best on those, because you're definitely going to need those for our next section. Because now it's your turn. Today you will be given a terrain to design an aqueduct for. There are 4 different options, and you get to choose which terrain you would like to build an aqueduct for. You will then design an aqueduct using Tinkercad or SketchUp to develop a 3D model. A quick note about SketchUp: if you are one of my students at College View Middle School, then you have learned to use SketchUp and you have it installed on your computer. And I know some of you prefer SketchUp because it has so many more options than Tinkercad. And so I do want to give that option to my own students. However, if you've never used SketchUp, never heard of it, then disregard that and just stick with Tinkercad, because we have spent the last few days mastering Tinkercad. Your aqueduct must maintain a constant downward slope. So, step 1 of this process is going to be to map the flow. So you will have 4 different terrain options, and you will choose one and then draw a gently sloping line so you can put where the water needs to flow below ground and in tunnels, or on the surface in covered trenches or pressurized pipes, or above ground on walls or arcades. So there's several different options for how to structure your aqueduct based upon the different types of terrain that you have and creating a gentle slope. My suggestion for this would be to open the document that has the 4 different terrain options, choose your terrain option, and then take a snip of it. And then once you've taken that snip, you can actually use the pen and your finger on your touch screen, and you can actually just draw that slope line so that you can have a clear idea of where your water needs to go in order to get from the water source to the town. So here are the examples. Here is scenario 1. So here is your spring. There's a deep valley, and there's a plain where you have a slight actual uphill elevation before you get to the town of Aqueductus. And so that would be one option. Another option, scenario 2, is where you have a very high reservoir, and then you have very varied terrain, all coming down into the town of Oceanus. So you can determine if that would be the scenario you would prefer. Here's a challenging scenario. You have your spring, and then you have the city of Rome here, and you've got a mountain peak, it looks like, and then you have your valleys and quite a high plain. So you would have to consider, where would you have to put tunnels and where would you need to put above ground features. And then the last one is scenario number 4, which is Giganticus water supply. So you're going from a spring at 390 feet and getting the water up to 410 feet. This particular one cannot be solved using only the elements that I'm teaching you in this lesson today. So this would be the scenario you would choose if you would like an additional challenge and have to do additional research, okay? So after you've chosen your scenario and your terrain, and after you have taken a snip of it and drawn your line where you best think your water needs to go, then you're going to move to step 2, and that's going to be learning about the different parts of an aqueduct that you can use to design your aqueduct. So the parts of an aqueduct are covered trench, tunnel, pressurized pipe, wall, and arcade. There is a document in your digital worksheet that will teach you all about those structures and how they work so that you can make the best decision. For step 3, you will open the checklist in your digital worksheet and work through each design step to create your 3D model. Remember that you will be creating the aqueduct in Tinkercad, or if you have SketchUp or learned SketchUp earlier this year, you can use it. And remember that you do have to create a model of the terrain and the aqueduct. to read through all the detailed instructions and the checklist that are in your digital worksheet for today's lesson. You will have access to all 4 design scenarios, and you can choose which one to use for your aqueduct design, and have fun.